Maintenance of plasma glucose is an intricate and coordinated process that requires input from the pancreas, adrenal glands, as well as the central nervous system. During fasting or similar dietary conditions, the liver becomes the most important organ in providing glucose to the bloodstream and restoring plasma glucose to their normal level. This essential liver function will provide glucose to tissues like the brain, red blood cells, kidney medulla, testes, and exercising muscle with the glucose they absolutely need. Plasma glucose is maintained somewhere between 80 and 100 milligrams per deciliter. This happens because of the effects of glucagon and epinephrine on the liver's glucose output. Under the influence of these two hormones, the liver's two pathways responsible for restoring blood glucose, namely glycogenolysis and gluconeogenesis, are both activated. By restoring blood glucose, the liver provides key tissues like the brain and red blood cells with the glucose they need as their major energy source. During fasting, the liver switches to using beta oxidation of fatty acids as an alternative energy source. When its needs of energy are met, acetyl-CoA in the liver begins to accumulate. That acetyl-CoA is then shunted towards the synthesis of ketone bodies, acetoacetate and beta-hydroxybutyrate. The importance of ketone body synthesis in the liver is that it provides a new energy source that is easily transportable in the bloodstream so it can be picked up by other tissues, whereas acetyl-CoA is not. Ketone bodies can be used by many tissues, including the heart, brain, and skeletal muscle, but not the liver. Beta-hydroxybutyrate and acetoacetate produced by the liver during fasting are picked up by extrahepatic tissue where beta-hydroxybutyrate can be converted to acetoacetate. Acetoacetate can then be further metabolized by the key enzyme thiophorase to form acetoacetyl-CoA. The donor of the CoA group is succinyl-CoA. Another CoA group is condensed by thiolase, which will produce two acetyl-CoAs that will then be processed through the TCA cycle and will produce 24 ATPs. But look here, that's the amount of fat reserves we have. 15 kilograms. That's nearly 20%, actually more than 20% of body mass is in the form of tags, essentially. This is tags. And look at the number of calories it can provide. 135,000, 5 times more than protein, and more like 140 times what the glycogen can provide in terms of energy. Lipolysis of stored tags in adipocytes begins with the activation of hormone-sensitive lipase in adipocytes. Hormone-sensitive lipase can be activated through the activation of the beta-adrenergic receptor by epinephrine or norepinephrine, resulting in the activation of adenylate cyclase, resulting in the rise in cyclic AMP, resulting in activation of protein kinase A, which in turn phosphorylates hormone-sensitive lipase. Hormone-sensitive lipase in the phosphorylated form is the active form. So the activity of this enzyme will be increased during the fasting state when both epinephrine and glucagon are elevated. Lipolysis of triacylglycerol by hormone-sensitive lipase produces 3 fatty acids and glycerol, which are then released into the bloodstream. It is noteworthy that hormone-sensitive lipase in adipose tissue is only activated by epinephrine through the beta-adrenergic receptor. It is not activated by the glucagon receptor because adipose tissue lack a glucagon receptor. It is also noteworthy that tags stored in adipose tissue represent a significant amount of fuel reserves for various tissues during fasting, and the lipolysis of these tags and availability of circulating fatty acids is essential for maintenance of the energy needs of several peripheral tissues during the fasting state. If you like this video, please subscribe. Thank you.